Good morning.
How you doing?
Kamal Dewan. Very good. You guys.
What's your name? Ferdinand? Ferdinand. Scott Hayes, nice to meet you.
Is this a skilled model of your modular?
Yeah. Data system, yeah. And talk a little bit about that.
Hi, how are you? Steve Lewis.
Steve, Scott Hayes,
Nice to meet you.
Hey, nice to see you. Kamal Dewan. Very
Steve
good.
Lewis. Nice to meet
You
you.
guys feel free to grab your line.
Sure.
So,
Let's ask me. Model.
containerized solution. Have its own flag.
Howard.
You look at it on Christmas.
So how long you guys been in this location?
About a year.
Not even a
Not even a
year.
year.
8 months.
Okay.
We used to be over at 300 South Becker, or the city tower. And we moved over here in like October. This office.
Gotcha. You guys been growing and staff?
Yeah.
Yeah.
Yeah. Andrew Sean.
Hey, Scott Hayes. Guys.
We used you guys as a basis of design for University of Kentucky data center. Never got it solved though.
Oh, yeah. Good enough.
Were you guys involved in that project at all? University of Kentucky? That's on the bell, not our territory, but it does not ring the bell at all. Kevin Duffy's territory. Was it on the list? Was it on the list?
I think I saw it.
Okay.
We had Active Power versus Vicon and another UPS manufacturer, anybody they wanted to partner with, Vicon. And it was kind of a political nightmare because the firm that recommended you guys must work with you guys all the time, stuff out of Texas. And they were gonna just fly in a flat spec Active Power. And it's a public university, and you can't do that. So we said, well, would you be okay if we provided an alternate to bid against Active Power? Yeah, that's fine. And then when we come down to it, Active Power didn't bid it. No bid, they decided to no bid the job.
Oh, okay. But they respect and they know they're,
Kind of left us out.
where we're at.
You know why?
I think they were probably all upset because we showed some objection to the flat spec. It wasn't really it was partially our objection, but it was mostly the fact that it's a public university.
I can't imagine, I cannot imagine respect or not respect, that's no big job.
Yeah, I'm not quite sure what all happened to that, but it ended up being Vicon teamed up with
80s, former MTV. Wow.
Yeah, it's, I don't know, but that's interesting. Was that in the last couple of years, or?
Yeah, it was last year, wasn't it?
Huh. We'll definitely, just because I'm interested in that, I just can't imagine us no getting a job, unless there was a technical reason why it didn't make sense.
There's one more activist for Tom. Should we wait for him or should we just get going? Okay. Well, I appreciate you guys coming. My name is Scott Hayes. I'm the regional account manager here for Active Power. I actually recently was with APCMG for the last 5.5 years as a system engineer and then enterprise account manager after that. Before that, I was with KJWW Engineering for the first 4 years out of college. So I have an electrical engineering background, I'm a licensed PE, and now with Active Power. I've got a 4-state territory: Illinois, Indiana, Ohio, and Michigan, that I've been basically in charge of educating, evangelizing the product, working with specifying engineers, design build, customers, running customers as needed, basically to support the Active Power main product and systems. So, and this is Kamal Dewan, he's Central Region Sales Engineer, System Engineer. He's been with Active Power about 6 years.
Yep, since 2006.
Yeah, so been out there working with engineers for a long time. Good name in the industry, very smart guy. Before I dive into the actual presentation, it'll help us to understand, I guess, a little bit more about the specific work you guys do out of here. I listed kind of the 3 main, verticals that we're in, but obviously education. There could be a data center within education, K through 12, or universities, things like that. These are the 3 verticals we do play well in and do a lot of work in. So what do you guys primarily do out here? Like, a lot of healthcare out of this office, data centers, all of the above?
It's probably 70% healthcare.
It is, okay.
We do have the next runner-up, I guess, would be higher education.
Okay.
Data centers is a market that kind of spills over from Madison a little bit.
Oh, yeah.
We try to do.
Mr. Johanning.
Mr. Johanning, and we try to do some more and more of it here, and that's really Tom's role, is to bring more data center work here. So we do a little bit, probably the less than 10,000 square foot size data centers. Guys would be chipping
Good.
Industrial, we don't do any industrial.
Okay, we'll get that. We'll definitely kind of cover the different applications within the presentation with that. I'm just going to give a brief overview of the company and then have Kamal run with the more technical overview and applications. Basically, we're based out of Austin, Texas. We do factory tours and hopefully we can use some PDH and some credits at some point, so we can get some more engineers down there. But Austin, Texas headquarters, we're also based in China. Over 20 years in the business. We started out as a magnetic bearing manufacturing company and kind of basically grew from there. We're an ISO 9001 certified manufacturing facility, so basically highest quality standards in manufacturing. Over 100 global patents in 40+ countries. We're coming up on, we should hit 3,400 flywheels in the market in the field by the end of this quarter. And over 120 million hours of field runtime. A couple big partners of ours, HP and Caterpillar as well. Who is Active Power? Well, we're basically intelligently efficient. We're going to show how we can reduce how we have a more efficient UPS and a lot of them out there via the nature of the flywheel system and the lower losses with the way we convert power and whatnot. Inherently reliability. We've done studies showing that in the case of the outages, the flywheel is 7 times less likely to fail in a battery system. Some third-party studies. And then also economically green. We definitely demonstrate a very reduced and drastic carbon footprint reduction. So we're really getting a lot of industry acknowledgement right now for our green and LEED certifications, certain LEED points right out of the gate with specifying Active Power flywheel in general. We've got 2 main product segments. We got our UPSs and then basically our powerhouse system, which is coming different flavors, 400 volt, 40 volt. Come on, talk a little bit more about that. Basically up to about a megawatt. Couples a jet engine generator system within the container itself with our active power plywood and some various other distribution controls, things like that. Who uses us? You know, we're definitely out there, and one of the fastest growing companies in IT right now, basically in infrastructure. This one should be pretty obvious from the previous slide. The company that ships most servers in the world, largest smartphone vendor, 5 major data centers that are tier 3 plus. Largest wireless carrier in the US uses us, third largest retailer in the world. 2 of the largest data centers in the world are active power clients. World's leading search engine providers, there's more than one, so both the big ones. Largest video game publisher, 4 of the Fortune 10 companies, 5 government contractors, 13 to 30 companies that make up the Dow Jones Industrial Average, 8 out of 12 major pharmas, and then branches of the military within the US and neighboring countries. Basically, this is a little bit outdated. Like I said, we're up to about 3,400. America's probably a little bit down because APAC is one of our fastest growing segments right now. But we still are growing in all markets just a little bit faster in Asia Pacific. And then finally, again, some of our core applications, data centers, healthcare, and industrial manufacturing. And we were just talking about how, the rest of these probably fit somewhere into the other pie, piece of the pie, just by the nature of the application as well. So that's a little bit about Active Power, where we fit and what we do. I'm going to turn it over to Kamal, tech genius, the products here to finish off now.
Sounds good, thanks Scott. And this whole presentation is obviously very informal, so if you guys have questions as we go, please interrupt me, throw darts at me. I talk really fast, so if somebody wants to slow me down, feel free to slow me down. So just overview on our product offering. The Clean Source UPS is really the heart of our business. We offer it from really 150 kVA, 130, 150 kVA, all the way up to 1200 kVA. Anything larger than 1200 kVA will parallel to achieve larger capacity on the same bus. Typically, we say we can parallel 7 1200s on the same bus. Typically, we rarely ever see more than 3 1200s because now you're getting above a 5,000 amp bus, 40 volts. So we do have quite a bit of paralleling capability. We also have another core product of ours, which we refer to as our GenStart module. What the GenStart module does is it takes protected 480 volt, 60 hertz from the output of the UPS, and it provides 24 volt DC or 25 coil crank amps to start your generator. So it just operates in parallel with your batteries, your starter batteries on your generator. Have anybody been familiar with the GenStart module? Have you guys ever specified it? I know some of the other affiliated offices I work with, we've incorporated them in some of the designs. So you guys have,
Yeah, we have received.
Okay, perfect. From a service standpoint, we have 24/7, 365 days a year. We have plenty of service capability around the globe. I want to say right now we're pretty much in every state, every major city. We have contracts in place where we can do 4 or 8 hour response. So good service coverage. Obviously, we sell under our brand, and you guys are also familiar. We also sell under the Caterpillar brand. And Caterpillar also distributes and services it globally as well. A little bit different value proposition between the two groups, but depending on what's best for the customer, determine what makes sense. But they're definitely a very, very good partner of ours. So just kind of an overview. Basically, the heart of our business is a 250 kilowatt flywheel. It's basically composed of a 4340 steel rotor that spins at 7,700 RPMs. In the event of an outage, UPS is going to go into discharge. Once your generator comes up to speed and voltage, we're going to synchronize with the generator, and we're going to walk the load onto the generator. So again, it's a 250 kilowatt wheel. Some of the major components of the wheel, basically you have the casting that houses the flywheel assembly. We have an upper and lower field coil, a 3-phase armature, the upper and lower bearings. Basically, there's no wear items on the wheel. It's pretty much a 20 to 25 year wheel. Once every 4 years, you will change the bearings on the wheel, and it's not so much that they wear out. What actually happens is over a long period of time, the grease starts to evaporate out of the bearing, so you can start to see lateral and axial vibration increase and bottom bearing temperature increase, but they're all trendable parameters. So there are systems out there that customer hasn't changed their bearings for 7 or 8 years, and they've been operating very reliably. But we do definitely want to take a proactive approach. I mean, we typically say once every 4 years you change your bearings. If you change the bearings once every 4 years, we know that you maintain an outstanding 6 9s of reliability. So we definitely are, we definitely take a proactive approach in regards to changing bearings once every 4 years. So typically it's spinning at 7,700 RPMs. We're always pulling vacuum. It spins in about a 5 to 20 millitorr environment, so very, very frictionless environment. We also inject a little bit more current in the lower field coils than we do the upper field coils, and what it does is it basically creates a magnetic unloading effect on the wheel. So even though the rotor weighs about 600 pounds, there's really only about 150 pounds on the bottom bearing. So again, it's spinning about a 5 to 20 millitorr environment. We're magnetically unloading the majority of the weight of the rotor, so you only see 150 pounds on the bottom bearing. And that's very important to us to really spin in a frictionless environment. That way, we minimize losses. Typically, it takes about 1250 to 1500 watts to maintain spin at 7,700 RPMs. So just to give you an idea how much that is, it's a 250 kilowatt wheel, 1500 watts. It's about a 99.5% efficient wheel. And I always kind of compare it to my wife's hair dryer, because she's got a hair dryer that says 1500 watts. And I'm like, I can spin a 600-pound wheel more efficiently than you can blow dry your hair. So, but it kind of gives you an idea for what the losses are. The UPS, as an integrated package, is about 97.6% efficiency. So there's some additional losses in the UPS, obviously from inverters, rectifiers. There's some fans. There's a very large choke in each flywheel cabinet as well. We'll kind of get into the topology. It's actually, this is actually a better picture of the buck. So you can see the upper and lower field coils, the casting, 43-44 rotor, 3-phase armature. It's actually a little bit better picture. And again, so once every 4 years, you're going to change the bearings. The other maintenance items are there's oil in the vacuum pump that needs to be changed once a year, and it's a mineral oil, so it's it's easy to dispose of. It's it's not toxic or anything like that. The other maintenance item is there's filters on the front of the unit, depending on how dirty the environment is. Most data centers are pretty clean, but it just depends on how dirty the environment is. But typically once a year, the filters are removable from the front. You take the filters out. You can vacuum them out or clean them out or even wash them. Typically, that's just done once a year. So once a year, you'll clean the filters, change the mineral oil in the vacuum pump, and then once every 4 years, you'll change the bearings on the wheel. And when you have a multi-module installation or multiple wheels, when you can isolate one wheel at a time, change the bearings, leave the other wheels online, protecting the load, and then move on to the next wheel. So you don't necessarily have to put the system in bypass for an annual maintenance or bearing change. So I'm not going to spend, you guys are familiar with traditional UPS topology. Spend a lot of time on it. You come in, your utility 100% of your power is AC. You convert it to DC. Off your DC bus is where your energy storage, VRLA batteries or wet cells. And then you convert back to from DC to AC back to your load. So typically, most traditional double conversion UPSs, they're getting better, but on average now, I mean, if you look at the 9395 or Liebherts, they're typically about 93% efficiency, at best, 93, 94% efficiency. And most of the losses are obviously in this conversion process, taking 100% of your utility, converting it from AC to DC, and then back to AC. Any questions?
I thought the 9350s were
9395 or the 9315s? 9395, they published 93, 94% efficiency on their data sheet. I've seen various, don't want to negative sell any competitor, but I've seen, various loads. I mean, if you walk in a data center, a lot of times data centers, even hospitals, imaging equipment, the UPSs are running pretty lightly loaded. So it's not, it's not unusual to see UPSs operating at 85% efficiency in real world applications. But the UPSs in general are getting more efficient. I mean, your traditional double conversion UPSs used to be like 91% was considered good. Actually, there was a study done and it showed about 12% of losses in data centers were in the UPS. So most of them are operating at pretty low efficiency levels, 5, 6 years ago. But they are getting more efficient. Probably 93 to 94% efficient is not unlikely to see at 100% load. I think Liebherr publishes 93.6% efficiency and Power publishes 94% efficiency.
Or 99 in eco load, which is basically taking that double conversion process out of it. So that's kind of that whole storage.
Yeah. Was that 99%?
On some of the new boxes, they have eco pop.
Yeah, eco.
Yeah, in eco mode.
Because they're not conditioning the power, they're just putting it bypass, basically.
Yeah,
Right.
right,
It's an infrastructure.
yep,
It's in bypass, but then instantaneously go to UPS.
yes.
Kind
And they
of
publish
short
within,
window transfer full cycle.
and they do publish it, you know, it's within the Sabima curve. The question is, you know, how many facility, you know, really critical facility like a data center, you know, we haven't run across a whole lot of facility managers or directors that are willing to operate their UPSs in eco mode, but I'm sure there's some out there. As well as, you know, an imaging equipment environment, you're probably definitely not gonna do that. You have high harmonic loads, you have sensitive equipment. And again, when you're in eco mode, I mean, you're basically in bypassing, you're passing through all the harmonics to the, you know, the line side. There's no, you know, there's no harmonic cancellation or anything like that. So you're, you know, you're basically in bypass with a little bit of activity, obviously, for converters. So this is kind of a high-level one-line of our topology. We are parallel online interactive UPS. So we come in AC, we stay AC along the entire critical path. We go through a very large choke in each flywheel cabinet, and we basically circulate all of the active currents, all of the harmonic currents across the utility inverter, across the DC bus, and back out to the main. We basically are using transient voltage surge suppression, or SPDs. We use line inductance. We use active control, bidirectional power converters and flywheel energy to correct all 9 IEEE defined power problems at this node right here. So, you know, you could have 50% total harmonic distortion for 100% linear loads. You'll see about 3% THD. If you had 100, you know, if you had 50% total harmonic distortion or 100% nonlinear loads, you know, you're probably going to see right around the 5% THD level on the input. We also have a very, very fast sample rate. So we sample on each phase 333 times every cycle. So once every 50 microseconds. So very, very fast sample rate. Basically, this guy right here, normal operating mode, he's basically acting as a variable frequency drive. And he's, you know, driving this flywheel always at 7,700 RPMs. And this is kind of a high-level drawing. This would be typical of what we refer to as our single module system, which is just a single 300 kVA UPS. We also have our multi-module system, which is basically you grow in 300 kVA increments. And basically, this is all of the critical components that you see right here, except for the bypass. All of these critical components are distributed in each one of the flywheel cabinets. So it's a very modular design. So in other words, if you had a 900 kVA UPS, every one of these, input contactor, 100% continuous duty SCR-based static switch, line inductor, both your IGBT-based power converters, your flywheel energy output contactor is in each flywheel cabinet, and so are the brains. So basically, each flywheel cabinet has its own brains. The way to really think about it is a bunch of 300 kVA UPSs in parallel. We also have basically a momentary SCR-based static switch on our bypass used in conjunction with a contactor or a breaker, depending on the size of the unit or the frame. The single module system, it's 400 amps. For the the multi-module system, it's the bypass is rated for 1600 amps because it's expandable out to 1200 kVA. Any other questions? As far as input voltage windows, very similar to traditional UPS. It's adjustable, typically plus 10 to minus 15% input voltage window. We're always regulating plus or minus 1%, 40 volts on the output. Anything outside that range, right, we're going to classify as an outage. So if we have to, let's say we program it at plus 10, minus 10% input voltage window. If our utility falls outside of that 10% window, we're going to disconnect from the source. Input contactor's going to open, and these contactors, this one's already open, this one's going to open. So you're going to completely disconnect from the source to prevent backfeed, and you're in discharge supporting your load until utility, your generator, your 40 volt, 60 hertz, or wherever you are in the world, 400 volt, 50 hertz, until that power returns and you qualify that source, you'll walk the load back onto utility. So very, very similar to a traditional double converted UPS from a continuous power sequence.
So there's no way, well, can you tell me if your bypass output is synchronized if you used a dual input source?
Yeah, so if you use if this was a dual input UPS, you have to, it has to be synchronized.
Okay.
It cannot be from two different sources. If it's coming from two different utilities, I mean, normally we get it from the same panel, but yeah, it definitely has to be synchronized.
Okay.
Yep.
Which is that's a common problem with all online UPS.
Yeah, online.
Some people, manufacturers have come back and said, well, our static switch acts as a device that as long as both sources are available, we'll cut the static switch in when the sine wave is in the right phase angle.
Yeah.
You won't see any change there.
Yep.
I'm not quite sure that works as well as they claim to.
make it work.
So again, this is kind of a high-level drawing. We have 3-line drawings if you guys are interested in seeing a 3-line of our system. But it's proven to be a very, very, very good technology. We do a lot of healthcare installations. I think we probably have about 300 hospitals in the U.S. We're doing Parkland Hospital right now, which is one of the largest hospital construction projects in the U.S. I think it's in Dallas. It's around 20-something wheels. It's definitely over 20 wheels. So it's a nice size project, combination of data center and big imaging suites. One of the nice things with healthcare applications and imaging equipment is imaging equipment tends to be pretty tough. You get high harmonic loads, you get big step loads. It's kind of hard to size your UPS when you're okay, we have 10 suites and we're gonna have these different pieces of MRIs, CTs, and X-rays, and so there's definitely some big advantages with deploying our equipment in that type of environment. Typically, when a UPS gets a big step load, or like an X-ray fires, a traditional UPS, double conversion UPS with batteries, there's a few main disadvantages. Is when you get that big step load, the DC bus voltage one tends to collapse. A lot of times the inverter's too slow to react, so your batteries get hit. And we're a piece of steel. We can take 100 hits a day. It's not going to degrade our wheel. The other advantage is we have a higher DC bus voltage, and it really allows us to handle that peak waveform. Typically, when a UPS gets a big step load, the DC bus voltage tends to collapse. If it collapses below utility, you guys might know this, but you end up with a waveform, that's chopped off. You end up not being able to really handle the peak waveform. So that's another big advantage. Also, utilities are very stiff source. So even though we have a very large choke in the middle of our, on our mains, in each flywheel cabinet, and basically that prevents any harmonic voltages from propagating from the input to the output, as well as harmonic currents from propagating from the output to the input. But it's also a stiffer source. So when we have X-rays fire, your inverter's not seeing the entire bulk power. So that's why we're able to handle, we have good overload capability as well. So it makes sizing, gives us a little bit more flexibility with sizing when we're dealing with imaging equipment.
What's the runtime on your UPS or on the flywheel?
It's 14.5 seconds at 100% load. And obviously if you have let's say you have a 600 kVA UPS, you can also add a redundant flywheel for redundancy or additional ride-through time. If you had a 600M+1, for example, it would be 21 seconds at full load, and it's very linear.
So when you say redundant, you mean you can connect 2 flywheels to 1 choke? What do you mean by redundant flywheels?
No. So when we add a flywheel, that's what I was going to say, one of the bigger advantages with our equipment, and I'll show you a lineup of a multi-module system, but when we add a flywheel, so we have an I/O cabinet and we have a systems cabinet that's kind of a central frame to the UPS. And then we can basically, what we have is referred to as a 300 expandable. So you'd start with a 300 kVA expandable system, and then you can add flywheel cabinets for redundancy or to grow in capacity. So anytime you add a flywheel cabinet, you're basically adding all of these critical components. And it helps from obviously, so when you're adding flywheel, you're either adding for capacity or redundancy or additional ride-through time. And typically, ride-through time is very linear though. So if you want to know how much time you get at 50% load, you get 14.5 seconds at 100% load, you're going to get about 28 seconds at 50% load, or 52 to 56 seconds at 25% load.
And also typically, how are these systems grounded?
So we always require a grounded Y input.
Okay.
And and we're not we're always grounded on the output, whether we're in normal online mode or discharge.
Do you work with high resistance ground systems?
Yes, we have, yes, absolutely. So that's it's an option on our equipment. And we do, we've kind of seen, it's obviously a 3-wire or a 4-wire plus ground system. And a 4-wire plus ground system, we really have what's referred to as a zigzag transformer on the outputs. We derive the neutral when we go into discharge. But a 4-wire plus ground system, you're going to run all 3 phases, the neutral, and ground to the UPS. And, in normal operating mode, we're basically, deriving the neutral at the source. So this is basically just kind of a high-level drawing of our bidirectional power converters and our flywheels. So we come out of our flywheel about 1,000 hertz, convert to about a 785 DC bus voltage, and then 480 volt 60 hertz if you're in the U.S. We also do some 400 volt 60 hertz applications in the U.S. We've kind of seen a little bit of a trend in that area, mostly in the data center arena. Obviously, we have 400 volt 50 hertz as well, depending on where you are in the world. Have you guys seen any 415, 240, or 400 volt? 240?
We've done three 415 volt data centers.
Okay, excellent. Yeah, we've done quite a few now too. We just actually did one of the largest utilities in the U.S., one of their new data centers in Southern California, and talking to some other guys that are going down that road. Have you guys seen any 480, 277, going 277 straight in the racks?
No.
New Dell servers, we're doing one of those right now.
Yeah.
That's power supplies are rated up right up to 277, so. Okay. So the Clean Source UPS corrects all non-IEEE defined power problems, and we talked a little bit about that, a little bit about how transient voltage surge suppression, line inductance, line capacitance, active control, power converters, and flywheel energy. And Scott does have a handout here as well. It talks about how we correct each one of those power problems in a little bit more detail in one of the handouts. Yeah, so if you guys are interested in that, there's a handout that goes through that. So again, a little bit on our size ranges. I know Scott already spent a little bit of time on this. So 130 to 1200 kVA for 480 volts applications. For 400 volt applications, we derate. In other words, we're really using the same frame UPS. It's, you know, if it's a 1200 kVA UPS, it's a 1600 amp frame at 400 volts. Obviously, we're still at a 1600 amp frame, so we have to derate the power level down to 1000 kVA. And the rest, Scott's kind of gone over that. So this is just showing an outage. This is just showing your input voltage going away, your output voltage staying smooth. This is just a snapshot. Basically, your input current goes to 0. You can see your output current. Again, so we have this, what's referred to as a single module system, and then a multi-module system. So really two main frames. The single module system is 130, 150 to 300. It's non-expandable. It's basically a one-box system. You have your flywheel energy storage in the bottom. You have your power electronics towards the top. You have a side cabinet with an option for a 3-switch maintenance bypass. And so it's just a nice one-box solution. We actually put a lot of these in hospitals because they never plan on having a UPS, for example, for imaging equipment. It's just a really nice footprint efficient box. I mean, it's 58 inches wide, 34 inches in depth. I mean, you can literally stick it in the corner. It's very nice from a footprint standpoint. Then we have our multi-module system, 300 kVA to 1200 kVA. Anything larger than that, we can parallel for additional capacity. And we can actually parallel different size units as well. The way to think about it is we're really paralleling, really load sharing across the flywheel cabinets, or what we refer to as the MMU cabinet. So if you had a customer says, I want 1500 kVA on one bus, you could parallel a 900 and a 600 and parallel to even 1500 kVA. Or if you had a customer that said 2100 kVA, you can parallel a 1200 and a 900 in parallel. So we're really flexible and have the ability to really grow in 300 kVA increments to whatever the power requirement is. So basically, this is a multi-module system. I know it's black, and that's really the color of the box. And it's it looks really it's a really nice from a visual perspective, but it makes it a little bit tough to see on presentations. But basically, what you have is I/O cabinet. We have a systems cabinet with a big touchscreen display. And then you have the flywheel cabinets. In the systems cabinet, each systems cabinet is basically, he's not a control cabinet, he's basically just a slave to the rest of the UPS. Again, all the critical components and all the brains are distributed in each one of these 300 kVA cabinets. So this guy's basically just tying them together. Inside the systems cabinet, you have an isolation disconnect switch for each one of these flywheel cabinets. So you get, if you want to do maintenance on this guy and leave the other 2 units online, you can isolate him via the isolation disconnect switches. So basically this would be like a 900 kVA UPS or a 600 M+1. There's no side access or back access with any of our equipment. One of the other advantages from an installation standpoint is there's a wireway that's not shown here that basically goes from the systems cabinet to the flywheel cabinets. All of the cables in that wireway is manufacturer provided, so you don't have a contractor that's having to provide cables to run them from your wheels to your UPS or battery, so it's a little bit of an advantage. And a lot of our multi-megawatt customers, they'll tend to put the UPSs back to back. Because it's AC back to the systems cabinet, it's very flexible with how you can arrange it in the room. You can have your I/O and systems cabinet in one wheel here, and you can have the other wheels across the room. You would have to do a custom wireway in that case, but it's all AC between the cabinets.
What's the heat output on those?
20,000 BTUs per 300 kVA, about. So if you had a 1 megawatt unit, it's about 80,000 BTUs, or 1200 kVA UPS, about 80,000 BTUs. So if you compare that with a traditional UPS, we should be about half to maybe even a third. So, a lot of times, we have on some of the further slides we talk about heat, but we basically operate between 32 and 140 degrees Fahrenheit environment. And a lot of times customers are like, oh, okay, well I don't need air conditioning. Well, as engineers, you guys know that's not true. I mean, UPS is putting off heat. If you don't have a way to remove that heat, or if you're not designing around that heat rejection, depending on the size of the room, it's possible that room will eventually heat up hotter than 140 degrees. Right?
So you don't need to necessarily cool. What's the ambient temperature that you can run in?
You can run it. We publish 104 degrees Fahrenheit. You can run it up to 100. The air intake can be 104 degrees Fahrenheit, but you have to, there's still gotta be a way to design around that heat rejection, because if you put it in a room and there's no proper airflow, it's gonna keep putting off heat. It will heat up hotter than 140 degrees Fahrenheit, but depending on where you're going, I mean, there's a lot of our customers that, they have like some industrial applications where they're just, huge, lots of facilities, and there's no air conditioning. They literally just open up the garages in front of somewhere to let it air out, and they've proven to be pretty robust. But you still got to look at it and say, okay, do I need to duct the air out of the room, some fans? Do I need air conditioning? Most of our data center applications, I mean, they're designing around cooling the UPS rooms. But from a cost perspective, it could be a significant cost savings to the customer because they're not going to use as much cooling infrastructure for their UPS rooms as they would for traditional UPS.
It's almost primarily because of comfort cooling, perspective at that point, making sure that we'll never go above 100, but targeting 80 or 90 even if you're not, nobody's allowing to move that's not typically adjusted, as needed for maintenance, things like that. That's where a lot of the cost savings comes in.
So basically, this would be our 300 kVA multi-module system, and you can expand as you grow. So a customer could start with, if their load was 400 kW today, they could start with a 600 kVA UPS, and they can add it flywheel cabinets as they need to, and then obviously we can parallel for additional capacity. So this is just kind of a high-level one line of a 900 kVA or a 600 N+1 kVA UPS. So you can see each of your flywheel cabinets houses most of the critical components. You have disconnect switches in the systems cabinet, and then you have your bypass in the systems cabinet as well. And there's an option there for a 3-breaker maintenance bypass with what we refer to as the G frame, which is up to 600 kVA. So, I know I said we have a single module system and we have a multi-module system. Within the multi-module system, we really have two frames. We have what's referred to as a G series, which is an 800 amp frame. It's expandable up to 600 kVA. You can add a third wheel for N+1, redundancy or additional ride-through time. And then we have our Z series, which is expandable all the way to 1200 kVA. So really 2 frames, and that's a 1600 amp frame. Main difference is with the G series, they look the exact same from the outside. If you look at a 600G and a 600Z, it's going to look the exact same. The main thing is just the bus works smaller. Obviously, it's 800 amps. You also have room for a 3-breaker maintenance bypass in the I/O cabinet. With the Z series, that's going to have to be in the external distribution, or we can also provide a 3-breaker. It'll be an external 3-breaker maintenance bypass. There's just not enough room in the I/O cabinet to fit the breakers. So this would be basically a 1200Z. So there's no room in here for a 3-breaker maintenance bypass, but same topology as the G series. So this is basically just showing an example of how we parallel. We can do basically a distributed bypass or a centralized. This is basically an example of paralleling 2 UPSs with a distributed bypass. So basically these input breakers will be in the same board, not the greatest drawing. These will be in the output. You have an output isolation breaker for each UPS, you have a tie breaker, then you have a maintenance bypass breaker. Pretty standard. I mean, if you're looking at power 93, 95 in one line, it's going to look the exact same when they parallel the UPSs. The main difference is we can parallel different size units, so that would be a 2100 kVA system. You're just going to load share across the 7 MMUs. So what's nice about this is that actually, if you have a 2100, this is a 2400 kVA system. If your load's 2100 kVA or less, you really have a good level of redundancy. You still have a redundant MMU. So this is Massachusetts-based M Technologies is are you guys familiar with M Technologies? Have you guys heard of them? So they do a lot of reliability studies for a lot of people in the industry. I mean, they've done it for us, done it for Cisco, EYP, Uptime Institute. I mean, they have a lot of different customers out there. And they actually did a study on our CleanSource UPS versus traditional battery-based UPS with VRLA batteries. And what they found was it was 7 times less likely to fail in the event of an outage. And it really came down to demand failures between batteries and mechanical energy storage. But interesting study. So I'm going to fly through a lot of these marketing slides. So typically we can get twice the power and half the space. We're operating temperature, again, up to 104 degrees Fahrenheit. We put out about half the heat, or 20,000 BTUs per 300 kVA. It's a pretty good rule of thumb. From a maintenance perspective, significantly less maintenance. Again, 1 p.m. a year, you're going to clean the filters and change the mineral oil in the vacuum pump, and then once every 4 years, you'll change the bearings. And actually, there's a really interesting study that was pulled together, and if you look at M Technologies data, you look at Tier 1, Tier 2, Tier 3, and Tier 4 data centers, And EYP did a similar study. It's an MTBF study, basically, on Tier 1, Tier 2, Tier 3, and Tier 4 data centers. And you look at EYP's data, M Technology's data, they have like, you get out in a Tier 3, Tier 4 data center, you're saying like 60-year MTBF. I mean, huge numbers, 80-year MTBF for Tier 3 and Tier 4 data centers. You look at like Tier 1 and Tier 2, they're still, pretty good, like 8 to 20 years MTBF. And then you look at the Uptime Institute's data on Tier 1 through Tier 4 data centers, and they actually, Tier 1 will be like 2 years, Tier 2 is like 5, Tier 3 is like 9, and Tier 4 is like 11, and you're like, okay, what's the discrepancy? I mean, EYP and M Technologies, or I guess HPCFS now, is, their studies are showing these huge numbers, and showing these data centers to be so reliable, and then you look at Uptime Institute, and it's, there's a huge discrepancy, and when you really look into it, it's, their studies are based on calculated MTBF of equipment. And for the most part, equipment operates pretty good. When you look at the Uptime Institute, it's based on real world data. And now you've kind of inserted, you've inserted human error, operating, parameters that may have been set incorrectly or whatever it is. The switchgear wasn't coordinated very well with the UPS systems, how they're defining an outage or whatever. But it's definitely an interesting study, because it's kind of one of the advantages that we pick with our equipment too, is, data centers operate pretty good to put people in all the time, and, having somebody to, not be doing any invasive procedures, once a year, basically going in there and doing an annual preventive maintenance versus, every, quarter you're having guys check every single one of those batteries. So there's definitely a reliability advantage just from a maintenance aspect. So efficiency, I know we talked about efficiency quite a bit, but typically we're about 97.6% efficiency. We also had EY, we just did a big factory witness test for a huge government job out west. It's a big federal data center, relatively new, and when EY hit our factory, and they were like, man, you guys are one of the only UPS manufacturers that hits your efficiency on the dot, your efficiency curves every time. So the efficiency we publish is 97.6 at about 100% load. And as you get down to about 25% load, I think there it is. So as you get down to about 25% load, we're still about 94% efficiency. So we're very, very efficient box. This is just showing, I'm going to kind of fly through this marketing slide, but this is just kind of showing an example of a cost comparison. Typically, we're a little bit more expensive up front than your traditional battery-based system, but we always get the payback within 2 to 3 years maximum. And we have some spreadsheets that you guys can use. I mean, or your customers can use. They can plug in competitors' numbers. They can plug in efficiency of their competitors' boxes, maintenance packages, and it'll calculate the total cost of ownership. So we're definitely very open with that and provide this to our customers as well, so they can play with the numbers. This is just basically showing the impact of having a high efficiency UPS, around 97% efficient versus traditional 92% efficient UPS. So you can see this is kind of a national average, 10 cents. I don't know what the utility rate is in the Chicago area. Is it anybody know?
7 to 11.
7 to 11.
Depending on where you're.
Got it. Okay, so assuming 10 cents, 600 kilowatt load, 8760 hours in the year, operating a traditional UPS at 600 kilowatts at 92% efficiency is going to cost about $45,000. Those are just losses. It's just electric losses in the UPS. It doesn't include cooling, maintenance, or anything else. And then operating 97% efficient UPS, 600 kilowatts of load, you're right around $16,000. So there's about a $30K delta, and that's why you really see efficiency. I mean, you guys have all seen the trend in efficiency driving the market. Is efficiency has can play a huge impact on your overall bottom line, especially for a data center or Colo. But even when you compare it with maintenance, I mean, a lot of times efficiency, is significantly, more, plays a bigger impact than even maintenance does. So. This is just showing lead material, so typically you can get lead points for buying clean source UPS under a few categories. So if you are trying to design a lead certified facility, there is potential for getting lead points, and we can explore that with you guys more if there's interest as well. From a monitoring standpoint, excellent monitoring capabilities, a lot of standard features: modem, Ethernet, SNMP, Modbus TCP, or 2-wire or 4-wire. Obviously, there's some additional options like remote static panel, remote EPO, RS-232, RS-485, and then we have our standard CSView software that ships with the equipment. It's very, very robust software. I mean, it's actually really, it's got a lot of different features. It stores up to 4,000 events. There's over 190 telemetry points that you can monitor everything from power characteristics to input power characteristics. All types of telemetry in regards to the flywheel itself, bottom bearing temperature, armature temperature, lateral axial vibration, vacuum, all of that. So it's very, very robust monitoring software. You download it on your, customer can download it on their computer, dial in via Ethernet. We can also dial in, if they'd like us to dial in, a lot of our customers will run a modem, maybe they don't want us on their Ethernet. They'll run a modem and we can remote monitor the UPS. We can send them weekly reports once a week. So lots of capability from a monitoring standpoint. This is just a snapshot, so it's kind of a typical setup for a customer. Maybe they want to see, system input, system output voltage. I always does that. One of the other nice things about it is this is the same software that the techs actually use in the field. They have, there's different level passwords, obviously, to access different data. But it's a really, really nice feature, especially during commissioning. I mean, we were recently commissioning a pretty big job out west, and it really gives us a lot of visibility into what's going on when there's, when time we have an outage, time the generator comes up to speed, how fast we're synchronizing, how fast we're locking on the load. We can download high-speed data capture plots. We can see exactly what's going on with the generator. Hey, your generator's overshooting. You need to dial down your ramp rate. So there's lots of nice integration features with this software. And one of the biggest advantages with our UPS, especially on the battery-free side, is we have some really critical. We have over 100 patents that are really critical and have really enabled us to have a really nice integrated solution. That's a huge advantage to us in the field. And we really end up with a UPS that's designed to be used with flywheels versus a UPS that's really designed to be used with batteries and you're putting flywheels on it, because there's lots of integration advantages that we get with our equipment that our competitors don't. A lot of those are, we have, integration features where we integrate with a transfer switch or switch gear. We refer to one as ATS command, which is a really critical feature. And so there's a lot of advantages with, also having a patent on the integrated flywheel UPS. We really have a much integrated solution versus having two vendors go to market and provide a solution.
Is your inverter ramp time integral to the your flywheel runtime? Let's say you're at 22 seconds posted runtime. Does that include 5 or 8 seconds of
walk-in? Yeah,
and
we never walk in the load. I mean, we team up with Caterpillar, Cummins, all the major generator manufacturers have good speed control on their generators. And one of the nice things with our UPS, I mean, it's designed to be able to get the load on the generator fast. I mean, we're not, some traditional UPSs, what we've seen out there is, they even have firmware. They have may even have like a 4-second delay before they even start walking on the load. And a lot of times, during commissioning, they're not really necessarily experts about designing around what's the difference between this UPS and batteries and this UPS and using flywheels. The nice thing with our techs and our integrated packages, we're really designing around flywheels. So I mean, when your generator comes up to speed in 9-10 seconds, by the time you reach 12 seconds of flywheel energy, it's a very good chance that all the load is already walked onto the generator. So when we specify 14.5 seconds at 100% load, we expect to make it on. We expect to have all the load on generator, well before we're out of flywheel energy. And the thing about walk-in is, like, 3 seconds of walk-in doesn't equate to 3 seconds of flywheel energy, because you're relieving the flywheel of load when you're walking the, when you're walking the load onto the generator. So you actually, it's really the area under the curve. So 3 seconds of walk-in only takes 1.5 seconds of flywheel energy. But typically, typical power sequence, 1 second outage or more, you're signaling the transfer switch, or you're signaling, start signal to your generator. Generator comes up to speed and voltage, 9-10 seconds. UPS synchronizes with the generator and walks on the load. Typically, that's 2 to 3 seconds of flywheel energy.
Okay, so what
Yeah,
happens?
3 second walk-in.
What happens to your flywheel if you expire your runtime during the walk-in?
Step load the generator. It's not going to drop the load.
I know, but what? And your flywheel continues to spin down after the unit goes into bypass.
As soon as it goes into bypass. So it's discharging from 7,700 down to 2,000 RPMs.
Correct.
So let's say it gets down to 2,000 RPMs.
Correct.
In the middle of walk-in. It's going to step load the generator. And now you're going to be on generator, your load's going to be protected by generator. The UPS is going to qualify that source, and it's going to start, recharging the wheel, basically. It's going to automatically come back online.
Okay.
And it's, once
Without human interaction.
Oh, no, yeah, without human interaction. I mean, typically after once you transfer to generator, you have, I'm going to say, 90 seconds to come up to speed. After 90 seconds, your wheel should already be up to full speed after a walk-in. And even if you don't complete the walk-in, you're maybe add an extra 20, 30 seconds to that.
Okay. That's
I
something.
couldn't imagine it being manual. I don't
That's
know.
something that you need to sell them harder. Your competitors are having difficulty with that.
Yeah, I didn't know that.
And it only really shows up during commissioning, because that's
Yeah.
when your commissioner is sitting there with the
At
stopwatch.
100%
And he
load.
wants to see
Yeah.
runtime. He doesn't
Yeah.
care about, the fact that you'll never get to that full load rating. He wants to see full load at full runtime.
Yeah,
Whereas, a lot of flywheels, or your competitors will give you that runtime,
Mhm.
but at the end of that runtime, there isn't enough flywheel left
Mhm.
to keep itself alive. Just spin down to zero.
Wow,
And then you do a retransfer
yeah,
from your gen back to utility. And you're expecting a little bit of ride through, you're expecting 3 milliseconds of ride through for that transfer switch to flip over. You got nothing because the flywheel's
Yeah.
at 0 RPM.
yeah, yeah. Yeah, I mean, typically we're.
And I think they've corrected that, but it's an option.
Yeah, and
If that's an option that you have to know to specify.
Yeah.
It isn't like buying floor mats for your car.
And I can tell you with 100% certainty, that's not an option with our equipment. I mean, it's guaranteed.
Okay.
I mean, as soon as we're on generator, whether we step loaded the generator, let's say we ran out of ride through time at, let's say we walked on 80% of the load, we're gonna put a 20% step load on the generator, as long as the generator, maybe the generator dips down as soon as we requalify the generator, which it should, it's not gonna, the generator can take a step load, it's gonna take 50. I mean, ideally, you don't wanna run out of ride through time and walk in. I mean, when we design a system, we wanna make sure all the load is walked on before we're out of flywheel energy. And we're really good at poking our nose into the overall design, sequence of operation. And we wanna make sure, who the generator manufacturer is, how long it takes for the generators to come up to speed. We wanna know who the switchgear guys are, how are they defining an outage, under and over voltage trips, under and over frequency, what the setting is when you're on generator, and we definitely design a system to be able to at 100% load work, unless there's some special conditions where customers like, hey, I'm never going to load it. Here's what I'm doing. I'm paralleling 8 generators on the bus. I need more ride through time. I can guarantee all these generators to be up in 18 seconds, and I'm never going to load my UPSs past 60%, even in a failure mode. We've run into occasionally things like that, but however the system's designed, we're designing the system to make sure all the load is walked onto the generator. But if it's not, we don't really care. But that makes, when I say we don't really care is, if you walk the majority of the load on and you're still you're putting a little step load on the generator, we don't really care, because at the end of the day, we're still making it, probably pretty easily, but sometimes customers are like, I ran out of energy before I walked all the load on, and they don't really, necessarily like that. At the end of the day, as long as it works, we don't really care. But when you transfer to generator, you're going to be on generator for at least 3 or 4 minutes. So hopefully you're not transferring back immediately to utility. Hopefully there's a delay.
Yeah.
Let your wheels
And that's up
recharge.
to the engineer to make sure we don't.
Yeah.
Ever get into that situation. It's just sometimes when a commissioner creates a commissioning report and that box doesn't get checked, that's all the owner sees.
Yeah.
It's an unchecked box.
Yeah.
And so then you're.
But that's pretty surprising.
Then you're trying to excuse your way out of a situation that will never occur.
Yeah.
However, why did you let the commissioner create the
Yeah.
situation if that'll never occur?
Yeah.
So that's just something you guys right now probably have the leg up on.
Yeah. Yeah,
just to-
I'm actually surprised that's not auto. I can't imagine that not being automatic. I mean, it seems like a risk.
The version we bought was not, and it just so happened the option became available after we had spec'd the unit and it was in production.
Yeah.
'Cause I think somebody else probably realized that
Yep.
this is something that's gonna not
Yeah.
be a good scenario. So.
Yeah. I may be going a little bit long on this presentation, but I'll just show you one of the other integration features while we're talking about it. It's important. I'll make sure this isn't permanent. Looks okay, looks safe. So one of the nice integration features that we also use with our flywheel is we have a feature called, with flywheels it's important when you're designing around flywheels, but we have a feature called ATS command. And what that does is it's basically, whether you're using, I'm going to assume this, we're using a breaker pair versus a transfer switch, but either one is fine. But basically, what ATS command does is just a couple 18 gauge wires that wires back to your gear. And basically what it does is it says it's a programmable feature. So if your switch gear, if your breaker pair, your transfer switch doesn't transfer for any reason, and this UPS is in discharge and the flywheels get down a certain percent energy, let's say 85% energy, we'll send a signal to your transfer switch or switch gear to say, hey, for whatever reason, utility's unstable, you haven't transferred, send us a star signal to the generator, we're going to transfer to generator. Where that comes in handy is if you have a transfer switch, for example, maybe it's existing and it doesn't have over voltage detection. Maybe you have overvoltage detection, maybe you have overvoltage situation, your UPS goes into discharge. With flywheels, you are limited around ride through time, so you definitely obviously you want to design around it. If you design around it correctly, there's no doubt you can build a reliable system. It's, if you're using a battery-based system, if not more reliable. So basically, you have overvoltage situation, your transfer switch doesn't see it, we're gonna go into discharge, and once we'll define that in commissioning. We'll say, okay, 80%. We know if we have 80% energy, that gives us enough time to transfer the generator and walk the load on. So that's a nice integration feature that we have that our competitors don't use. And it's important when using flywheels, even if you do have a transfer switch with over and under voltage detection, what if you're getting a bunch of short-term hits and you have a program to transfer after 1 second, but you're never getting a full 1 second outage and you may be depleting your wheels. So this is a nice feature to say, hey, we're, for whatever reason, utility is unstable or in the process of failing, we want to go ahead and start the transfer process. So it's a nice integration feature. And obviously, we always want to coordinate an outage, by the same parameters as our transfer switch, right? So if this is set at +10, -10, we always want this guy to be, let's see, so we would always want this usually to be consistent or a little bit wider. This guy always needs to be equal to or tighter. In other words, if this was at -20, that could be a bad situation. You could have a -15% low line condition. This guy doesn't see the outage and this guy's into discharge. So it's always important to define an outage by the same parameters, under, as well as with frequency as well.
Yeah. Actually, with it kind of works backwards too, where if you're on generator, you don't want the transfer switch to retransfer back.
Exactly. Mm-hmm.
You put an inhibit signal there to say, hey, my flywheel's not up to speed yet, please don't.
You can absolutely.
That's what we use to pacify the commissioner on that particular project, even though it's kind of a...
Yeah. That's part of our ATS command feature too. It's like, hey, you're not allowed to transfer back unless this guy's happy, and that means he's discharge enabled, But typically, we're recharging back. We're getting back up to being discharge enabled within like 20, 30 seconds. And even after a full transfer, we may still have energy left to discharge if something was to happen, but not a lot, right? So, but typically when you're on generator, you're gonna be on generator for 10 or 20 minutes
Sure.
before you transfer back.
Sure.
Trying to think if there's anything.
But if there was any event along the way that
Sure.
like you said, the transfer switch parameters were not aligned with UPS parameters, you could be discharging, recharging,
Yeah.
recharging, and then
Yeah,
timeout occurred, and then now you're.
I've seen a 10 megawatt site have no overvoltage detection on any of their transfer switches. And they had half of our equipment on one side and half battery-based systems on the other side. And all the battery-based systems dropped the load, even though they had plenty of ride through time. They had an overvoltage situation that lasted a couple hours. We had ATS command integrated on our feature. We had operated perfect on our side. UPS had discharged for 7 to 10 minutes, and that was on the other side. And that was the end of it. By the time they found out what was going on. So it's a really nice feature, even for battery-based UPS. Won't give it away. I know I'm running out of time. I'm going to fly through some of these and.
Yeah, your gen start's probably not too critical.
Yeah.
Cat pushes it sometimes, depending
Yeah.
on the application.
That's pretty much it, I can start, right?
Yeah, I'm just gonna spend just 2 minutes. Am I running along? You guys need to get back? Not about 5 minutes or?
Yeah, we can go over just a little bit.
Okay.
Let's do it right now, so we're not too
Yeah.
quiet.
So in this presentation, we'll give you a copy of this. There's just some, high level. This is kind of tier 1, tier 2, mostly data center focused, a tier 3 design. This is another design. This is isolated redundant configuration. I know we don't have a lot of time. This is a very typical large installation of ours. We don't do a lot of massive amounts of paralleling. We do a lot of distributed redundant systems. In this case, we have 4 primary gens and a swing. We'll bring them all, in event of an outage, we'll bring them all up at the same time. If any one of these isn't up to speed and voltage in a certain amount of time, we'll close that swing to the bus. And we also monitor them as they come up to see if anyone's lagging, significantly.
You do
There's some-
medium voltage?
No, we don't have any medium voltage UPSs, but we do have medium voltage installations where we're generating at medium voltage. But at some place we got to step it down,
Yeah.
and if we're going to parallel massively at medium voltage, we need to understand what that ride through time is. It's not to say we can't do it,
Yeah.
but it's more challenging. Like this is actually a medium voltage down to 415, 240 volt installation,
Okay.
but the generators they're not in parallel. Even though the runs are all medium voltage, we actually basically integrate our UPS. This is basically like a medium voltage PDU. So
Do
we're
you guys
going
run at 600 volts at all, or is it only 415?
415, 480. But this is a medium voltage installation that we did, and there's actually 4 phases of this. This is a big 3 to make 2 design via static transfer switches. So you guys can look through this. These are some of our big customers. It's a big Yahoo installation. Terramark Culpeper. You can go out on YouTube and type Terramark Culpeper. This site's actually designed around 110 900s and 55 2 megs, all distributed redundant type design. And there's a few other ones. Data Bank in downtown Dallas, Colo. University of Texas on the Longhorn, so I always put this up anywhere I go. But we do one of the most critical data centers, Rescale. That's pretty much it. I'll let Scott close it out.
Yeah, I appreciate your time, we won't keep you any longer. There's just a few items on the table. I left a CD here, I don't know if you have a place that you can put the CDs, but I'll bring some engineering binders when I receive them. Stock and shelf with those. Do you guys keep paper binders still?
We do for the UPS.
Okay, so I'll bring those for now. The CD has everything more on it. So I don't know who's in charge of that, even those, but then there's just a few flyers. You know, the powerhouse, we don't really need to explain that. It's pretty self-explanatory. It's basically a generator with the same container as the UPS with all the necessary controls and jet started stuff. So we pretty much covered everything. You guys, you know, take my cards. I live right here in Chicago. If you guys need any additional information, run it through me. You want validation on application for Flywheel, you know, project assistance, whatever. I'm discreet about your customers, things like that. Just give me a shout and you know, let me know what you need. Okay. Any final questions?
Do you pre-test these at the factory, or do you do that on site? Is the enclosure there set up?
We do site commissioning, but it's all, we build it right at the site.
Whose gen are you using, and that Cat's?
Cat will come in. It's customer driven and lead time driven.
You guys used to be partially owned or wholly owned by Caterpillar, right?
No, we've actually never been owned by Caterpillar. I mean, we still have an OEM agreement. Caterpillar's an important channel of ours. I mean, where they, you know, really support, you know, a lot of territories are very proactive, and we definitely support them in those territories. And, you know, overall, they're a good partner. It's really more of an OEM agreement where they take our UPS and, you know, they'll brand it under the Cat brand, and they'll distribute it and service it globally. They have obviously very huge network of dealers, good service organizations.
Why is it, and I know this is a competitive question with the ecosystem, why is it, what's the drawback of using the ecosystem using the cash?
You know,
You said pass-through, but.
Power Eco Mode?
yeah, we
The
did.
9315 or something?
Or 9395.
9395, yeah, that's correct.
I have a great one line on this, but this is not a good one line of a double UPS. It's really high level, but basically in eco mode, I mean, you have your static, you know, you have your static switch, right, that wraps around here.
Right.
You're basically just, all of your power is going through the static switch. In the event of an outage, you're switching back to online, basically. So every time, you know, one of the drawbacks may be you're step loading your inverter every single time. There are some very high-tech engineers out there that said they have tested them and they're not. There's a possibility they're not within the Sabima curve. It depends on the outage. You know, opening and closing a breaker sometimes is a pretty easy outage. You know, if you have a really hard sag or something like that, is it really within the Sabima curve? And then there's some engineers that say that it's actually not. We know of a very large customer on the West Coast that had to actually take their equipment. They didn't pass the Sabima curve test, and they had to put them back online. But anyways, the point is not to negative sell. I mean, there's some efficiency advantages, obviously, with it. I think some of the drawbacks is, it's still relatively new, and some customers, or if not most, are still a little bit uncomfortable. I mean, they're operating their UPS basically in bypass. So there's definitely no harmonic cancellation. I mean, you're passing all the harmonics back to the rest of your facility. So if you look at that too, it's like, what's the impact to the rest of your facility too if you have a really high harmonic load? I mean, transformers and other, over time, what does it really look like? And what does your entire system efficiency look like? I mean, are transformers and things like that running hotter in other parts of your facility? If you're not really, providing that isolation to, prevent harmonics from propagating through the rest of your facility. It's definitely an interesting approach. We happen to be in a pretty unique situation because we're an online UPS and we're already 97 to 98% efficiency. So we feel pretty good about already being at 98%. It's not, there's no real drawback. And I think even the eco mode guys are really between 98 and 99%. And depending on what energy storage they use, if you're going to put, for example, if you're going to put flywheels off the DC bus, you're going to reduce your efficiency overall by 1% anyway, so you're kind of back in the same boat as we are from an efficiency standpoint, and you're operating offline. And there's other concerns with doing that if you transfer back. You have interest across the east and west. I don't want to get into negative selling. I can only do that internally.
I mean, I spent 5 years at APC, was selling APCMG. We respect them. There's applications for flywheel, there's applications for batteries. Sometimes you could look at one or the other. Obviously, we're not going to tell you to use a flywheel for every system, but hopefully you recognize some of the value, inherent value in the space savings, carbon footprint savings, things like that, and in the fact that you can design a very, very reliable system around flywheel based on the parameters we give it, which is help you guys to engineer, and we support you guys on that. So APC, Mitsubishi, Toshiba, they're all good companies. We all have our pros and cons, and ups and downs, right? So
The affiliated office that comes to mind that's probably done a lot of our equipment, the one that comes to mind, I think there was another one that did a lot of work too, but the one in Phoenix, Arizona, they do all the Banner Health, or a lot of the Banner Health.
Rob Condra?
Yeah, Rob Kendra, I know Rob, I've met him before. Yeah, someone said hi if you're talking.
Yeah, I know him and I had a discussion about your product a few years back.
Yeah, very good.
who should I, final question, who should I contact about for next time I come in about, or talk to the binder option?
For me, yeah,
Okay.
let's give you my card here.
Okay, thanks a lot, guys.
Thank you very much.
Yeah,
Thank you very much. Would you like me to send, or Scott send a copy of this presentation?
That'd be great.
Yeah,
That'd be great.
Yeah, we've been doing, we've been trying to do a much better job, ramping up our sales organization to really deal with some more people in the engineering community. We've,
Yeah, it seems Chicago was kind of not weak by active power, but it just seemed like it was.
no, the Midwest. Midwest has been weak.
That's why
That's why Scott's here. Yeah,
All right.
that's exactly right.
I'll sugarcoat it. No pressure on you.
West Coast and East Coast, we've had lots of, we have big Terramark installations and lots of stuff on the East and West Coast, and it's slowly starting to move in. Actually, Texas is a really good state.
My dad went to.
Oh, really?
He still works at KJ.
Oh,
Down
okay.
in the office right over here, actually.
Oh, yeah?
I was going to ask you if
Yeah.
you were related.
Yeah, so he used to run the Bass office, now he's working right here.
You guys aren't gonna kick him out of the office, or KJW.
They are one of our chief competitors.
Yeah, I know.
They overcharge
There's enough work
you
for all three of us.
$7 on your credit card.
Okay.
So there's $7 and some change cash.
Yeah, thank you very much for taking the time.
That the restaurant gave.
Oh,
Okay?
thank you. Back.
Yeah, they gave it back because they charged your credit card.
I gotcha.
So they just put it in an envelope and it's yours.
No problem.
Okay.
Thanks a lot.
What size do you go up in this container?
To a megawatt.
Really a megawatt.
A single container, you can get up to 480 kW, just.
So you're using your 1200 paired up with a 1 megawatt?
Well, it depends on how much short break load there is. So there's some, there's kind of our standard configurations, but we have a lot of kind of custom enclosures because it just depends what the customer wants. But that would be an example of a 1 megawatt generator with a 600 kVA UPS. So there's obviously, there's room for short break load. I mean, it's kind of more of a data center type application, or that's what's driving those at least. And then you have, obviously some critical load as well. So maybe 400 kW mechanical and say 500 kW critical.
It's the beauty of the system, obviously, when there's just no more room in the building to do.
Yeah, that happens.
Yeah.
Cheaper.
That happens a lot.
Yeah.
More people that don't see the merits of building a brick and mortar data center. They want a temporary ride through for their.
Yeah, they could be leasing.
I know
something,
higher
they don't
ed.
take with them,
Higher ed seems to be doing more and more containers. I know we bid on a container job for what was it? University of South Carolina.
Okay.
And it was because the grant money was there now. They needed the data center for research that was based on what the grant money was funding, which was the research piece. And, it takes to hire an engineering firm and an architect and then get the building on the ground, you're talking 5 to 7 years. Whereas they got the money right now.
Yeah.
They need the data center this second. And so I understand where they're, I'll take your
You want to take that? Yeah. No, yeah, I'll come back with binders at another point. Yeah, this is, I mean, we're the only ones I know of doing the flywheel with, coupled with a generator and a single tested system, so, since it's, pre-tested, pre-commissioned all together, you basically, kind of set it and forget it, is somewhat the aspect, just since the maintenance is so low on these things.
Yeah, and you don't have to worry about keeping the battery at 68F.
Yeah. Those are small ACs, they're fully redundant to each other, but they're just big enough to, cover the small load in there.
Yeah.
Pretty much all our enclosures we do that. We don't want anybody to get hot while they're working, that's a really,
Yeah,
it's our text, it's the influence of our service crew. Thank you, thanks. I'm really shocked that there's a project that we know did. Had to have been a technical.
No, that's-
Or we lost it.
I know.
Because if we had, I can't even think of engineering